Thanks, Ricardo. Can all of you hear me properly? Okay. So this talk is about denoising. I'm going to explain, and there are connections to Ricardo's talk in the morning, and of course optimal transport and empirical base. I'm going to explain all of this. Now I know this is a diverse audience, so please feel free to interrupt me at any point of time. I don't have to complete my slides. If you have any questions or comments, please let me know. Okay? So I'll start. So this is based on two papers. The first paper is joint work with Nicolas Garcia Trilos. And here is the problem. So I'm going to talk about denoising. So I should first of all define what is denoising. And I'm going to define denoising through a very simple latent variable model. So now the notations have changed, but it is similar to, as I said, Ricardo's framework. I have z and theta coming from a distribution, joint distribution. Z is what I observe. Theta is my latent variable of interest. Theta has a prior distribution. I call it the prior distribution, but it is really the latent variable distribution. And z gives, so first of all, you draw theta, which you don't observe, and then you corrupt theta by some likelihood. That's my likelihood. Think of this as the normal distribution with mean theta and variance 1. So I'm adding Gaussian noise to it. And then I observe z. And the goal is to recover the latent variable theta from the observed z. So that's the problem of denoising. Okay? So as I said, I'm going to assume that the likelihood is known. This is different from Ricardo's talk in the morning. And this is a simple model. And as I said, examples could be I have this likelihood can be normal, Poisson. So these are location examples. It could be scale examples also, uniform 0 theta, normal 0 theta, this is scale. My primary objective is to try to understand theta and its distribution G star, which in most real applications will be unknown. But the first part of the talk, when we set it up, I'll assume that G star is known. So obvious examples are Gaussian mixture models. So suppose G star is a discrete distribution with k atoms. Then I have k clusters, and my observations are z's. And as I said, the goal is to denoise z, which means to get rid of the noise in z and to estimate or predict the latent variable theta. Is that clear? That's the goal. So in this very simple formulation, you can ask to predict. So the goal is, in this model, I want to predict theta given z. What would you like to do? You would like to have a function delta of z, which you would use to predict theta. And you would imagine that delta of z should be close to theta. So you can look at a loss, which is the squared error loss. So this is your loss of estimating theta by delta of z. And the loss is random. You take an expectation, you get the risk. And you may say, I want to find an estimated delta which minimizes this risk over all possible estimators. Okay? And most of you may recognize this, that this is a very simple solution to solve. The answer is actually the posterior mean, right? All you do is condition on z, and then you can minimize that for every z, and this is the quantity that minimizes this Bayes risk over all estimators delta. Is that clear? Right? So now I want to, my notation for the posterior mean is theta bar of z, which is just the expectation of theta given z. Z is my observation again, theta is what I want to predict. And this is the form of the estimator. So you can say, so all I have done so far, I've shown you a benchmark and I've shown you the best thing you can do in the Oracle setting where I know G star. But this talk is about constrained denoising. I would not be giving this talk if that is what I all wanted to say. So I am now going to point to you some drawbacks of this posterior mean. And that is hopefully going to motivate the constrained denoising that's going to come. Okay? So all I have shown is in this very simple latent variable model, the best thing you can do is the posterior mean. So here is an example. Now, quite often these denoising problems, what you get is you don't get one z and theta. You have multiple z's and thetas, and you want to estimate all the thetas. So here is one of the simplest examples you can construct. Theta, suppose, has a prior. Suppose normal 0, a is 1. So the prior is normal 0, 1 in red. So these are my 60 unknown thetas that I do not observe. I observe the z's corrupted by noise. So it's normal theta 1. I observe the blue points. okay? And my goal is, given the blue points, can I predict the red points, right? That's the goal of denoising, the way I'm saying it. And now you can say we have already shown that the best estimator is the posterior mean. The posterior mean are the black points. And I want to plot this to you to show that, do you think that this group of red points are well approximated by this set of black points? And that is the starting point of my talk. And I'm going to make the case that maybe not. They are, of course, ideal from the squared error loss sense, but they seem to be shrinking a little bit too much. And that is going to introduce, and I'm going to motivate the OT-based denoiser, which will be the first main big thing of this talk. Okay? So it's obviously true that these black points, which are the posterior means, is actually an overshrunk estimate of the theta is. Why is that? Of course, this is a normal model. You can write down the posterior distribution of theta given z. You can compute its posterior mean. You can very easily show that theta bar of z is basically z over 2. And marginally, z over 2 has normal 0.5 distribution. Why? Z marginally has normal 0.2. Okay, so this is the marginal distribution of normal. So obviously, you wanted to estimate something that has a distribution normal 0.1, but if you use the Bayes estimator, you are predicting it by something that has normal 0.5. So there is a shrinking effect. Now this is not only happening in this particular example, it's very easy to see by using the law of total variance that the variance of theta is the variance of the conditional mean of theta given z plus the expectation of the conditional variance. So this is always non-negative. So you can always see if you use the posterior mean to estimate the theta, then the variability of the posterior mean is going to be smaller than that of the original thetas. So the case I'm trying to make here is that the posterior mean, although is the right thing if you fix your idea as minimizing the squared error risk, it has this drawback. And we want to address this drawback. Yes?
Just out of curiosity, when you say you wanted to approximate red, do we care particularly, are the points, do you care particularly about the points or just the distribution of the points?
Very good point. And I would like to say the answer should be both, right? And what the Bayes estimator is doing is it is not caring about the distribution, it is just caring about the denoising each point. But ideally, you'd like to do both. Okay, that's a great point. Any other questions or comments? Okay, so now what I'm going to do, and the OT-based denoiser is somewhat natural now. So you can say, okay, I want to minimize the squared error risk, but I can try to make sure that I do not distort the distribution of the latent variables. That could be a very reasonable goal, and that is exactly what my orange points do. Okay, you can see the distribution of the orange points are very similar to the distribution of the red points, and I am now going to claim that these are better denoised points than the black ones. Okay, and I'm of course going to formally define and characterize. That's going to be the first part of my talk. But I also want to say that you may think that, okay, I'm doing this, but then I am matching distribution, but maybe I can lose a lot in terms of predicting each one of them. And this is a plot of the risk which shows, so I'm just plotting the risk of 3 estimators. The most naive thing you can do is to estimate theta by z itself. That has constant risk 1. You can look at the Bayes risk or the Bayes estimator that has the smallest possible risk, that's the black line. And what we do is the orange thing, which closely hugs the black line. So I'm also trying to make a case that this kind of has a good compromise. It matches the distribution without losing a lot in terms of risk. Is that clear? Is that clear to everyone? Yes.
It's much more complicated to compute.
Sorry?
It's much more complicated to compute.
I'm going to talk about the entire description and characterization soon. Okay? Now, here is another drawback of the Bayes estimator. So now imagine I have all my theta i's lying on this circle, uniformly distributed on this circle. I don't observe the theta i's. I observe theta i's with Gaussian corruptions. I observe the blue points here. If I do, and of course my G star is the uniform distribution on the circle. If I look at my Bayes estimator, all the black points are the Bayes estimators. They're all inside the circle. This is going to happen, right? If you have the distribution supported on the circle and you're taking averages, you're going to always lie inside the circle. And I'm trying to make, and it may be situations where you would not like that. You would like to retain the circle. So, of course, if you know G star, our OT-based denoiser will map all these points back to the circle. Okay? So I also want to make the point that the Bayes estimator is not good at capturing geometric features of G star. Is that clear? Okay. So now some history. When we started working on this with Nicholas, I thought this is quite natural, but we couldn't find the rich history that now we have been able to dig up. So by the way, as you can also anticipate, that I'm just setting up the problem. I am assuming G star is known. The most interesting case is when G star is unknown, and that's the second part of the talk, where I use ideas from empirical Bayes. And I'm going to explain that. But this problem was known to astronomers more than 100 years ago. The astronomers do a lot of denoising. They look at stars, they take measurements, they have measurement errors because of the fact that you are looking very far distance, but they can calibrate the systematics, how good their telescope is, and so on. So for every observation, they also have a measurement error, and they would like to denoise. So Arthur Eddington is actually a famous astronomer who noted even in the 1940s. So what astronomers were doing was they would estimate, they realized that the Bayes estimation is the posterior mean is the best thing to do. They would estimate this by some method. And then they would interpret that these estimated posterior means are like my theta i's. And they would quite often treat the distribution of these this estimated posterior means as a good estimator of G star. And all I'm trying to make the case, which is what Arthur Eddington also mentioned, that this is not the case. In the statistics literature, as far as we could see, Lewis had a paper in 1984 where he basically realized that, look, here we are looking at an ensemble of parameters, as he called parameters, and then you would like to have estimates whose distribution, and he called it the histogram, should be a good estimate of the histogram of the parameters. So that is essentially where OT comes in, and we are trying to solve this problem. So in the statistics literature, after this, there have been various attempts, particularly this paper by Ghosh, but I think they did not have the tools of optimal transport, so they couldn't give an explicit solution to this problem. Okay? Okay, so let's now get back to our proposal. So as I said, I have this very simple latent variable model. I'm assuming G star is known for the time being. I want to still minimize the squared error risk, subject to the constraint that I don't distort the distribution of my denoiser, right? So you may think, okay, this looks like an OT problem, right? And of course, what I'm going to do in the first part of the talk is talk about its existence, uniqueness, characterization, and so on, okay? If a unique solution exists, we are going to call that the OT-based denoiser. That's the first part of the talk. So here is my rough outline. I'm going to talk about the characterization and existence of the OT-based denoiser. How do we implement it in finite sample theory? Because in reality, you never really know G star. That will happen through empirical Bayes techniques. And then I'm going to show you a drawback of this approach and propose another variant called the variance constraint denoising. Is that clear? Any questions? I'll pause here for a minute to take any questions. Okay, so I guess this is a slide I don't have to go through. This is just an introduction to OT. But all I want to say is that we will look at different costs. So here I highlight the quadratic cost, but in this talk we will see slightly different costs. And I will say that T transports nu to nu tilde in this notation. We all know the Kontorowicz's relaxation. So instead of finding maps, now we are looking at joint distributions. We know this is a linear program, very helpful in computation. The one result that I would like to highlight, in case some of you are not aware of this. So, of course, this is called Kontorowicz's relaxation, where I'm looking at maps, at transport plans or couplings. And that seems to be a relaxation, but if you know that your source distribution, nu, has a Lebesgue density, then the Monge problem and the Kontorowicz's problem have the same solution. Not only that, the optimal coupling is basically induced by a map. This is very basic optimal transport. So all I want to say is that there is indeed a gradient of a convex function that pushes my source distribution nu to nu tilde, and it's unique as soon as I assume that nu has a limit density. Is that clear? Again, I'm being a bit, I'm going through it very fast, but I hope everybody is aware of this. Good, good. Okay, so let's now go to the computation of the OT-based denoiser. So here is the problem I wanted to solve, right? I had my likelihood model, I had a prior, by prior I just mean the latent variable distribution, and there is a distribution, G star, which I don't observe. I want to solve this problem. Minimize the quadratic risks subject to this constraint. And you might say, okay, this looks awfully like a Monge problem, but not yet. So some notation, the marginal distribution of Z, I'm calling it mu. So that's a marginal distribution of Z. Okay. See, if instead of theta there had been a Z, then this is just typical Monge problem and we would be done, right? But how do I solve this problem? The first thing you realize is that you can add and subtract the posterior mean. So you add and subtract the posterior mean in this, and then you use the most famous inequality or equality in statistics, a plus b whole squared is a squared plus b squared plus twice ab. And then you realize that the cross product term vanishes. And you have this term which does not depend on delta. This is the only term that depends on delta. So you realize if I want to solve this problem, it is the same as trying to minimize this over all possible deltas. Is that clear? Right? So this is the problem I want to solve now. Now again, if you look at it closely, if only there were no theta bar, if this was Z, I'm in business, just typical Monge. But this is also an optimal transport problem with a different cost function. So all you do, instead of the cost function, say theta minus Z, I have theta minus theta bar of Z. Right? So this is the cost function, and then this is essentially an optimal transport problem, a Monge type formulation with this modified cost function. Do we all see this? Right? So now we can bring to bear all the machinery we know about from optimal transport. I also want to highlight, which will become relevant later on, this cost function is interesting because, see theta bar, although I do not highlight it, the theta bar depends on G star, the underlying latent variable distribution. Right? It is a posterior mean. So I want to emphasize that this cost function actually depends on the prior G star. Okay? Is that okay? So now here is the first result. I have to assume I'm doing optimal transport, a quadratic type cost function. I need a second moment assumption for theta. And I want to have a transport map, so I'm assuming absolute continuity of Z. I also need an absolute continuity of theta bar of Z. Then I can show there exists a unique solution delta star to this problem. So this is the problem I wanted to solve, right? I wanted to denoise, I wanted to estimate theta by delta of Z such that you don't distort the distribution of the priors of your latent variables. And this is exactly the problem. We have already seen that this is the same as this problem. And now I'm saying under just these two conditions, there exists a unique solution. And you may ask now, what is this unique solution, or how is it characterized? And now we should know that optimal transport maps are essentially gradients of convex functions. So if there was no theta bar, this would have been essentially a basic Monge type problem, and I know the solution should be the gradient of a convex function at Z. Now all I am doing is essentially I have theta bar of Z composed here. So that's the only modification that one needs to make. Okay? And you can also imagine what is theta bar, what is the gradient of the convex function doing? You have the posterior means, and then as if that does not satisfy the distributional constraint, and then you move it to satisfy the distributional constraint. So the gradient of the convex function that arises is basically an optimal transport map that looks at the distribution of the, so theta bar push forward mu is, note, is the marginal distribution of Z. So theta bar push forward mu is basically the distribution of theta bar Zi's. And so these are my distribution of the posterior means that does not equal G star. I'm just making that happen. So no wonder if in the picture you realize, so this is theta bar zi's. They do not satisfy the equality of this distribution. I just do an optimal transport to make this and this have the same distribution. The same thing is happening here. So every point now here is just pushed in a way so that the distribution of the orange points is the same as the prior distribution. Is that clear? Is that clear to everyone? Okay, so the black dots are transported to the orange dots via the gradient of a convex function. Okay, so this is the first result, that you can actually characterize it quite easily. Any questions? Any questions or concerns? Yes. I don't think it's sort of a projection. Okay, I have a one slide proof heuristic. Maybe that will help you clarify what's really going on. So as I said, again, this is the starting problem. I wanted to estimate the theta by delta of z, subject to this constraint. I add and subtract theta bar. I have this problem now. Now, this is the Monge type of problem. I can write down the Kontorowicz's formulation. So instead of maps, I'm now looking at couplings. So the marginals are mu and g star, mu and g star. And this seems to be like what the Kontorowicz's relaxation should be like. Overall plans now, overall joint distributions. Now, of course, we have to show this. Now, to study this, an intermediate step that arises is, okay, so you can try to understand this quantity. You can write it down in this quantity. So that's essentially this quantity. And now you realize that look, if all I am doing is, so here I have mu and g star, but in the cost I have theta bar of z, right? So let's look at the distribution of theta bar of z. That is just theta bar push forward mu. The infimum over this, so I can replace this by the y here and bring this in the constraint. As soon as you do that, you realize this is exactly a typical Kontorowicz's problem. I have assumed absolute continuity of this distribution. So by Brenner's theorem, there is a map, and there is an optimal coupling, which is basically induced by a map. That's a gradient of a convex function that transports this distribution to this distribution. So essentially, you know that the optimal coupling has to be like this, right? And then you can also show that this also has a unique solution, and if that has a unique solution, that is exactly the delta star I want to compute. So essentially now comparing these two, I know that delta star has to be gradient of phi for a convex function phi composed with theta bar. Does that make sense a little bit? Okay. So the proof is just, so here's the crucial step. I'm just taking this and writing the distribution as this. It's fairly simple, actually. Nothing very profound going on here. Is that okay? Okay. So now, so far we have assumed a hard constraint, right? I want to explicitly make the distribution of delta z to be exactly g star. But you may want, suppose you want a soft constraint. So you want to still minimize the square error loss or risk, but you want to now penalize the distance between delta push forward mu and g star. So you can imagine if tau goes to infinity, right? If tau goes to infinity, then I am giving very little weight here. So the solution would be just the posterior mean, right? Would be the posterior mean. If tau goes to 0, then I'm giving enormous amounts of weight here. So this will become a hard constraint, and this would converge. Delta star tau would converge to the OT-based denoiser. Okay? You would expect that. In fact, you can actually solve this explicit problem, and you can show that this penalized version has an explicit expression, which is a convex combination of the posterior mean and the OT-based denoiser. And it's such that these two limiting behaviors happen. This is just another easy problem. Yes.
Is it clear that the Wasserstein distance is the right metric you want to use to make this
It's very good.
constraint? Because, like, if I'm thinking of your circle example, if I actually want to recover the original support of G star, I want a metric which is actually
very good point.
You know, the Wasserstein, it's not sensitive to support, so it's not going to.
Yeah. this school expression would not exist otherwise. So,
Okay, so that's the motivation.
so that's just the motivation, that if you use this penalty, you get a very easy expression. Yeah, you're absolutely right. You can play around with other regularizations too. Okay, so this completes the first part. So all I have shown is there is a problem with the posterior mean. I have shown you that here's a natural thing, natural fix. Now I want to talk about estimation. Okay? So in estimation, by the way, so this is joint work with my postdoc Adam at Columbia and Nikos Ignatiadis, who's an assistant professor at U Chicago. So this is the title of the paper. We thought we would finish it before this talk, but that hasn't happened, unfortunately. Hopefully in a week. Okay, so let's wrap up again. Simple denoising setting. I want to recover theta. The oracle, now you will realize and probably appreciate why I call it an oracle, because this assumes that G star is known. And this just gives you a quantity that we can try to mimic in the sample, but we can never compute because we do not know G star. And now the question is, can I try to get close or approximate delta star using samples? Okay, so now I give you many, many zi's coming from this model. Of course, I do not observe the theta i's. And I want to approximate this oracle denoiser. How do I do that? Yes, Shiva.
Can I ask a question about what you were talking about before? It's fine here. Just in terms of what do you lose by enforcing this constraint? Is there like some quantification?
Yes, I will. I'll give you a result on this. Actually, so actually, okay, so maybe I don't know if I have this result here, but we can prove a result like in terms of the base risks. Of course, the base risk will be smaller than the risk of this, but we can prove that this risk of the OT-based denoiser is upper bounded by twice the base risk. So it's between the base risk and twice the base risk. So I think this is what you wanted, right?
Yeah, that's exactly.
Okay, good.
That's for any G star.
Anything. Any G star. Okay. Good. I don't know whether I have that in my slides. Okay. But maybe not, yes. Okay, good. So is the question clear now? I want to approximate this quantity from the samples. And the strategy we will employ, and this is where empirical Bayes comes in. So empirical Bayes, so okay, first of all, there's nothing really Bayesian going on here. I'm still calling it a prior, but to me a prior is just a latent variable distribution. And empirical Bayes is just trying to indirectly or directly estimate the prior or the latent variable distribution. So G star is the prior, I want to estimate it by G hat. And once I estimate the prior, I can essentially use the same technique by plugging in this estimated G hat. And that is the approach I'm going to use to estimate. Okay. So now, of course, estimation of G star is what is called the deconvolution problem in statistics. And it's a hard problem. You can solve it using Fourier methods. I prefer typical empirical Bayes maximum likelihood methods, and I'm going to talk about the maximum likelihood approach here. Okay, so what is the, so now I have said that to be able to estimate this oracle denoiser, I need to estimate the prior because theta bar depends on the prior, right? I don't even know what is grad phi star, so we have to estimate all of this. And the idea is I want to just first estimate the prior. So let's suppose you know that the prior belongs to some class. It could be a fully non-parametric, it could be the class, it could be any probability distribution in Rn, or it could be a parametric model. Suppose you know it's normal 0A, where A is unknown. Anything, parametric, non-parametric, you can do anything. All you have is the data, right? And note here the data is actually also IID. And what is the distribution of the ZIs? ZIs is this mixture distribution, right? So this is the joint, and you integrate out theta, you get the marginal for Z. So this is the mixture distribution of the ZIs. So you only have ZIs, access to the ZIs, and you note that indeed the ZIs carry information about the prior because the density involves G. So all you can do is just to maximum likelihood. You have a density for your observations, you have IID data, just write down the likelihood and try to maximize it over your class of models. And the beauty is, okay, by the way, empirical Bayes has also a long and rich history. Robbins, this is the Robbins from Robbins and Munro too. Herbert Robbins in the 1950s just claimed that this could be done. Kiefer and Wolfowitz in 56 showed that this leads to consistent answers. In the statistics literature, there's a huge body of work. Bruce Lindsay studied a lot of things about the characterization of NP-MLEs. Computation is discussed in this book by Boning. And I think in the last 10, 15 years, there's a very interesting, very profound result by Jiang and Zhang, which has kind of given this field a lot of impetus. So you can actually do this. This is meaningful. This is somewhat different from what Tudor was showing, because in Tudor's case, he had a parametric class with k being the fixed number of components. Here, I don't even assume that. This is an infinite mixture. I want to maximize the likelihood over all possible distributions. And the fact is, this is actually a convex program. You can solve it, and this has some nice properties. Okay, so I will not talk about so much about that, but this is going to be my main way of estimating G hat. Sorry, estimating G star. Okay, so let's get back. I wanted to estimate the Oracle denoiser. The Oracle denoiser had this form. So by the way, what is this gradient of convex function? This gradient of convex function arose from this coupling, right? So the coupling is supported on a graph of a function. And this is the coupling. So we looked at this Kontorovic's type problem, theta bar. Note that theta bar involves G star. And I have a coupling between mu, which is the distribution of the zi's, and G star, the distribution of the latent variables. And these three quantities are unknown to me in general. So what would a very simple plug-in approach do? I want to first of all estimate theta bar. Suppose, how do I estimate theta bar? Theta bar was the posterior mean with the true prior. I have estimated the true prior by G hat. I just plug it in. So this is essentially a sum if G hat is discrete. In fact, the NP-MLE gives you a discrete output. So this is actually a sum. This is very easy to compute. And this is a very natural, naive estimator of the posterior mean. And at the heart of empirical Bayes is this result that although the prior suffers from slow rates, as has already been pointed out, deconvolution is hard, the posterior mean can be estimated at a very fast rate. And that's one of the most powerful results in the theory of empirical Bayes. Okay? So, by the way, so this I hope sounds reasonable, right? I just estimate the prior and I plug it in and I have the posterior mean. So I can estimate theta bar. Now you look at mu. Okay, I have IID measurements from mu. So I just replace mu by mu(n), the empirical distribution of my data. Okay? I have G star, which is the unknown prior. I have again estimated the prior by G hat. And to me, this is a problem you can actually solve. Usually, G hat is discrete with very few atoms. So this is actually a very simple linear program to solve. Is that clear? So this is the problem I want to solve. I have a coupling. So this pi hat coupling can be thought of as an estimator of pi star. But my goal is not pi star. My goal is the map. This coupling need not give me a map immediately. But then I play the very simple trick, which is I look at the barycentric projection of this coupling. Okay? So the idea of barycentric projection is that note, indeed, if your coupling is of the form of a map, I can recover the map by looking at this conditional mean. So I fix the first coordinate and look at the conditional mean, because of course this is a map. There's only one value it takes, so the mean will be exactly that value. But this is what happens with pi star. Pi hat need not be induced by a map, but you can still look at the barycentric projection and you get an estimator delta hat. Okay? And the case I'm trying to make is that delta hat would be a reasonable estimator for delta star. Is that clear? Okay? Good. Okay, so here is some picture. And this is the picture where I had many points drawn. So the latent variables are drawn from the circle. I add Gaussian error. I have a lot of variance. So it's very difficult to even see that there was a circle, but just because the error variance was very large. If you do the Bayes estimator, I've already shown the problem with the Bayes estimator is all the denoised points will be inside the circle. That's what you have. Of course, the Bayes estimator is also an oracle quantity. It assumes the knowledge of the prior. You don't know the prior. If you do empirical Bayes, you get this as your estimate. This is is not bad, I must say. Because as I said, the method I described has essentially no tuning parameters, and it still captures the shape reasonably well, I would say. Now, this is the Oracle OT-based denoiser. Like the OT-based denoiser, at the Oracle level, you would have these, and you would just push them back to the circle, but you do not know the circle. So you have to now, in some sense, estimate the circle using G hat. Now, there is a result that G hat, the prior, estimating the prior is a hard problem. Deconvolution is hard, and the G hat gives these point masses. So it looks kind of bad, and then the barycentric projection also essentially gives you the same points. So I would say this is okay, reasonable, but you see that here I have emphasized I'm trying to recover the prior more. Here there is no emphasis on recovering the prior, but I think these points lie close to the circle. This is an enormously noisy example. Yes.
Hey, can I ask a question about the previous slide? So now that you do barycentric projection, you end up with a biased estimator.
Yes, of course it's biased, but you can still show that delta hat would converge to delta star.
Sure, and is it also biased when you assume that the G star is known to you?
No, if G star is known, then there is then pi star is induced by a map, right? So then the barycentric projection is just exactly the map. So I don't understand this. Sorry.
Yeah, so I'm saying, I mean, here the bias comes from the barycentric projection step, and if you don't need to do that, under the assumption that G star is known, that you still, then like MMSE estimation, you get back to unbiased estimators.
Okay, unbiasedly estimating transport maps, I think is very difficult. Transport map is essentially estimation beyond one dimension is a non-parametric function estimation problem. I don't think you can have unbiased estimators. So, and the rates are non-parametric and so on, unless you make, I guess, simple parametric assumptions. So, I don't know. Shiva and Tudor have worked on this problem a lot, so I don't know if they want to add anything. But I would say that unbiasedness is not necessarily the issue. I would say anything you do would be biased. Like in non-parametric function estimation, any reasonable approach is biased. But a little bit of bias can be good because it reduces variance quite a bit. So that's the whole idea of non-parametrics, right? Is that okay? Okay? Okay, so now here is the result in that direction. So now, so as I said, this is this. So I first of all find the coupling by solving this optimal transport problem, this Kontorovich's relaxation type of problem, look at the barycentric projection, and I get an estimator for delta star. I have a bunch of conditions. The first two you had already seen. Just for the existence of maps, I need some conditions. And then I have a similar condition as Tudor. I am using a one-sided version of this. And all I need, if you realize it, you see, first of all, there are two things. I am kind of basing everything on how good the estimator for the true posterior mean was. So I need the estimator for posterior mean to be reasonably good. And then also I'm solving this deconvolution problem. And what we can show, in some sense, the rate of this depends on the maximum of the two. And I'm going to now explain. So rate of convergence is dictated by how well the Bayes estimator can be, the Bayes estimator can be approximated, and how well the prior can be estimated. Yes.
Can you remind us what's a typical scaling of Rn that we should expect?
Exactly. Next slide. Good point. Good point. Any questions? Okay, so I should just go to the next slide. And as I said, so let's now focus on a particular case, the normal location mixture model. This is a multivariate case. The covariance matrix is assumed to be known. Then Rn is essentially 1 over n. And this is, as I said, this is really why empirical Bayes is so powerful. Estimating the prior is very bad. It's logarithmic. But estimating the prior, the posterior mean is super fast. And this happens to 2ED's formula and so on. So in a sense, you see, Rn is like 1 over n, Qn is logarithmic, so the slower rate dominates. Qn dominates. Okay? And as I said, this is, to me, one of the most profound results in this Jiang and Zhang. By the way, this Zhang is Chunhui Zhang at Rutgers. And this is very, very non-trivial. Means there is no reason why the posterior mean should be very well estimated, but it is indeed the case. Using this plug-in approach, this NPMLE approach. Okay? So of course, in this particular case, if you use a very non-parametric setting, you suffer from deconvolution rates. And that's going to kill you. And that is why the picture was kind of bad. If you say that this is bad, yeah. Because you are the error is basically because of deconvolution. Because you're directly estimating the prior here. Okay? And the nice thing, again, to highlight the power of empirical Bayes, you may say in the posterior mean too, I'm estimating the prior. But somehow that effect is not present. Okay? Is that okay? Is that clear? So let's now, how much time do I have, Ricardo? 8 minutes, okay. So now with this, as you have seen that here the dominating rate is going to be the deconvolution rate, can we do something better? So here is the idea of variance constraint denoising. So okay, look, trying to match the whole distribution is just too difficult. Let's just try to match the first two moments. So the problem I want to solve is I want to still estimate theta by a function delta of z, which minimizes the risk subject to the constraint I don't change the mean and variance of the underlying prior distribution. Okay? And this is the problem that I'm trying to solve now. This is not immediately an optimal transport problem, but I'm going to also show it is actually an optimal transport problem. Okay? So as I have said that the main rationale is we know that the Bayes estimator obviously shrinks, right? So the variability of the Bayes estimator is going to be smaller than the variance of theta, and I don't like the fact that this is less than or equal to, I want to make it equal to. That is what I have here. Okay? So I want to now give you a proof of existence, characterization, and so on, and I want to go through this proof because it kind of is a cute proof, goes through the Bush-Wasserstein space. So now this is the problem I want to solve, right? I have a minimization like this with the two moment constraints, okay? And I wanted to talk about a Gaussian optimal transport problem where I have u and v, where u is normally distributed, v is also normally distributed. I match the first two moments of u to match the first two moments of delta of z. The first two moments of delta of z are e theta, variance of theta, u has e theta, variance of theta. And then theta bar of z, I have v, which matches the first two moments of theta bar of z. So the mean of theta bar of z is, of course, e of theta, and the variance is variance of theta bar of z. Okay? And I want to show that these two problems are the same. How do I show that? So first of all, I show that this problem will have a larger value than this Gaussian optimal transport problem. Of course, in the Gaussian optimal transport problem, you realize I'm minimizing over couplings which are, of course, jointly Gaussian. Okay? So what do I do? So suppose I give you a feasible delta. Take any delta that satisfies these two constraints. Okay? What do? I want to give you a joint distribution of u and v. So I look at the joint distribution of u and v, where I essentially look at the variance covariance matrix of this object. So I've given delta, this is a valid variance covariance matrix, this is a valid joint distribution. And now you look at the objectives. Term by term, if you just expand this, the first two moments of delta of z match that of u, the first two moments of delta bar of z match that of v, so the objective values are the same. Yes?
Yeah, is there a typo on v? What should be the mean of v?
The mean of, so v is mimicking delta bar of z, right? So the mean of the posterior mean is just the mean. See what I mean? So it is the same. Does that make sense? So all I'm saying is expectation of theta given z is expectation of theta. Okay? Good. 5 minutes. Good. So I have now shown that the right-hand side is actually smaller than the left-hand side. But I know how to solve the right-hand side. I know there exists a transport map, and this transport map was alluded to in Ricardo's talk as well, where all you do is basically it's an affine transformation. So to transport v to u, all I need is an affine map. So T is a matrix. I multiply V by this matrix, and I have the optimal transport map. So this this matrix now tells me what the optimal delta should be. I just keep the same formulation, replace V by delta by theta bar of Z, and now I can show that the left-hand side, which is this problem, right, is less than or equal to the right-hand side. Is that clear? Because for this map, I have the optimal coupling. That's the right-hand side. And this is some delta. Here, there was an infimum over delta. So both sides are the same. And I know the exact characterization of the variance constraint denoiser, which is obtained through this simplification. So now you can basically solve this. And this is the solution to this problem. And now you can think about given, here is the result. Oh, sorry, I was actually wrong. That was for the distribution. This is for the variance constraint. That's the 2R here for the variance constraint, sorry. Okay, so now what I want to do is I have this estimator, which is an oracle estimator because it depends on theta bar. I want to estimate this particular denoiser. Okay, so how do I estimate? So I have 3 minutes or so. 3 minutes, okay. So the last thing I'm going to talk about is how do I estimate this denoiser, this oracle denoiser. Okay, it's actually very simple. So here's just a pseudocode. So if you look at the Gaussian setting, right? So what are you doing? You again have to estimate the posterior mean, and I will use empirical base to estimate the posterior mean. I have to estimate the variance covariance matrix of the posterior means. If I have an approximation of theta bar, I can just use the sample covariance matrix of the estimated ones. So m hat is now an estimator of this quantity. I already have an estimator for theta bar. I already know how to estimate the expectation of theta. That is just look at the average of the average of the zi's. All I have to now tell you is how do I estimate the variance of theta. This is a Gaussian model. Variance of z is variance of theta plus sigma. I already have samples from this. I know this, so I can compute this. So this is basically now a plugin, very simple plugin approach. You can compute this and delta hat variance constraint estimator. And here is the picture. That now you really, this shrinks too much. You want to de-shrink it by a linear transformation. And it just changes it to be like this. And now you can compute its rate, and as you can imagine, this is a simpler problem. Here the dominant term will be, as soon as you have 4 moments for the prior, the dominating term will be how well can you estimate the posterior means, and through empirical base we can estimate the posterior means at almost a parametric rate. So here now the rates become almost parametric. So again, you can generalize this idea. Why do you want to match only the first 2 moments? Why not other moments? Why not I give you some functions phi L? Why not you match the moment for phi L and so on? You can do all of that. You can show when it has a unique solution and so on. But I don't have a time for that. I'm just going to end with. So this talk is about starting with the posterior mean and saying it has some drawbacks. It shrinks. I want to fix that. I have the OT-based denoiser to do that. I've studied characterization, computation of that OT-based denoiser. The rates of convergence for delta star can be slow. I have also considered the variance constraint denoiser, which matches the first 2 moments. Thank you very much. Thank you. Thank you.